Good morning, everyone. I am going to present to you the topic of operating systems and intern design principles. So here we have chapter one. We're going to review the computer system overview. So we'll be using content from William Stallings, the ninth edition. Um, so let's just get into it. Exactly what is the operating system? The operating system provides a set of services to system users. It exploits the hardware resources of one or more processors, and it manages secondary memory and input-output devices. So the basic elements of the operating system include the processor, input-output modules, main memory, and a system bus. The processor controls the operation of the computer. It performs the data processing functions, and it's referred to as the central processing unit. The main memory stores data and programs. It's typically volatile. The contents of the main memory is lost when the computer is shut down, and it's referred to as real memory or primary memory. The input-output modules. What do? They basically move data between the computer and its external environment. For example, secondary memory disks, devices such as disks, communication equipment, terminals. These are these are devices that move information between the computer and its external environment. Now, you may be asking exactly, what is the system bus? The system bus provides communication among processors, main memories, and input-output modules. As you can see here, a top-level view of the computer components. Here you have the CPU, which is comprised of the PC, the input-output, PC stands for program counter, the IR instruction register, the MAR memory address register, the MBR, the memory buffer register, the IOAR, that's the input output address register, the input output buffer register, and the execution unit. And of course, the system bus, which connects the CPU, the main memory, and the input output module. The input output module has the buffers. The main memory consists of instruction registers. The microprocessor. Oh my goodness, I look so okay. So the microprocessor is an invention that brought about desktop and handheld computing. It contains a processor on a single chip. It's the fastest general purpose processors it has multi-processors, and each chip or socket contains a multiple processors or cores. The graphical processing units, GPU, provide efficient computation on arrays of data using single instruction multiple data techniques pioneered in supercomputers. They are no longer used for just rendering advanced graphics. They're also used for general numerical processing, for physics simulation for games, and computations on large spreadsheets. The digital signal processors, they deal with streaming signals such as audio or video. They used to be embedded in input-output devices like modems, but now they're becoming first-class computational devices, especially in handhelds. They're used for encoding or decoding speech and video codecs, and they provide support for encryption and security. Those are digital signal processors. As I said, they deal with audio, They deal with streaming signals such as audio, OPC, or video. Now let's get to system on a chip. To satisfy the requirements of handheld devices, the classic microprocessor is giving way to system on a chip. Other components of the system, such as DPSs, GPUs, input-output devices such as codecs and radios, and main memory, in addition to the CPUs and caches, are on the same chip. Now, that is really something. So let's go on to the instruction execution. A program consists of a set of instructions stored in memory. The processor reads or fetches instructions from memory, and the processor executes each instruction. 2 steps. So for the basic instruction cycle, we have a start, then we fetch the next instruction, then we execute that instruction, and then we have a loop back here where we go back to the fetch stage. From the execution stage, we go back to the fetch stage, and they fetch the next instruction and execute the next instruction. And then eventually they may halt until all instructions are carried out, and then you come to a halt. For instruction, fetch, and execute, the processor fetches an instruction from memory. Typically, the program counter holds the address of the next instruction to be fetched. The program counter is incremented after each fetch. The instruction register is loaded into the fetch instruction is loaded into instruction register. The processor interprets the instruction and performs required action. The processor memory, processor input output, the data processing, and the control. Here we have the instruction format, the integer format. The program counter is the address of instruction. The instruction register instruction being executed, the accumulator, which is like a temporary stage. All these comprise of the internal CPU registers. Then a list of partial opcodes. They load AC from memory, they store AC from memory, and 0101 adds AC, add to AC from memory. So that's a partial list of opcodes. So all this comprises of a characteristics of a hypothetical machine. So now let's move on to examples of program execution, contents of memory and registers in hexadecimal. So as you can clearly see, we have a fetch stage and an execute stage. Sorry about that. Step 1, fetch. Step 2, execute. Step 1, step 3, fetch. Step 4, execute. Step 5, fetch. Step 6, execute. So let's move on to interrupts. Mechanisms by which other modules may interrupt the normal sequences of the processors are known as interrupts. Now, they're provided to improve processor utilization. Most input-output devices are slower than the processor, so the processor must pause to wait for the device. And of course, this is a wasteful use of the processor. So what do? We implement interrupts. Now, there are different classes of interrupts. There's a program interrupt generated by some sort of condition that occurs as a result of an instruction execution, such as arithmetic overflow, division by 0, attempt to execute an illegal machine instruction, and reference outside a user's allowed memory space. There's timer interrupts, which is generated by a timer within the processor. This allows the operating system to perform certain functions on a regular basis. We have input-output interrupts. It's generated by an input-output controller to signal normal completion of an operation or to signal a variety of error conditions. And you have hardware failure, which is generated by a failure such as a power failure or memory parity error. Now, as you can see here, we have flow of control without interrupts. So this is when there are no interrupts. And here we see the flow of control with a short input-output wait. And here's what it looks like with a long input-output wait. And we have a transfer of control via interrupts. And now we have the instruction cycle with interrupts. Now we start, fetch the next instruction, execute instruction, interrupts disabled, interrupts enabled, check the interrupt, initiate interrupt handler. Then we, from the interrupt stage, go back, fetch the next instruction. And of course, we have the hold stage, of course. So this is the instruction cycle with interrupts. Now the program timing with short input output wait. This is without interrupts, and this is it with interrupts. Program timing for long input output wait. Here we have, okay, so I'm just gonna give you a second to just appreciate and digest this diagram. This is what it looks like without interrupts, and this is what it looks like with interrupts. A program timing with long input output waits. Fun stuff. Higher operation processor waits and the output operation processor concurrent with processing execution. Hardware, software, simple interrupt processing. Device controller or other system hardware is used as interrupt. Processor finishes execution of current instruction. Processor signals acknowledgement of interrupt. Processor pushes PSW and PC onto control stack. Processor loads new PC value, program counter value based on interrupt. And then moves on to the software component. The save remainder of process state and information. Processor interrupt, restore process state information, and restore all PSW and PC. Sweet. Hmm. So this was a simple interrupt processing figure. Cool. So figure 1.11 illustrates the changes in memory and registers for an interrupt. Let's just zoom in here. Hmm. Processor, memory, control set, start, service center, button, users program. So interrupt occurs after instruction at location N, program counter, general registers. Okay, control step. Interrupt service routine, users program. Okay, sweet. So changes in memory and registers for an interrupt. Sweet. Multiple interrupts. Multiple interrupts occur while an interrupt occurs while another interrupt is being processed. For example, receiving data from a communications line and printing results at the same time. There are two approaches. They disable interrupts, disable interrupts while an interrupt is being processed, and use a priority scheme. Let's take a look. Sequential interrupt processing. Oh my goodness, this PC. I saw this coming. Stop playing the game. Oh my God. So let's go interrupt handle X, interrupt handle Y, use a program. Sequential interrupt processing, and you have nested interrupt processing. Use a program, interrupt handler X, interrupt handler Y. Transfer of control with multiple interrupts. Sweet. Okay. Cool. And this here is an example of time sequence of multiple interrupts. So user program, printer interrupt service routine, communication interrupt service routine, this interrupt service routine. Sweet. Memory hierarchy. Design constraints on a computer's memory. How fast? How much? How fast? How expensive? If the capacity is there, applications will likely be developed to use it. Memory must be able to keep up with the processor, and the cost of memory must be reasonable in relationship to other components. Memory relationships. The faster access time, the greater cost per bit. Greater capacity is equal to smaller cost per bit. And greater capacity equals slower access speed. The memory hierarchy. Going down the hierarchy, here you have inboard memory, which consists of registered cache and room memory. You have outboard stage, which include magnetic disk, CD-ROM, CD-RWs, DVD-RW, DVD-RAM, and Blu-ray. And then you have the offline storage, which consists of magnetic tape. Now, in the memory hierarchy, going down the hierarchy, we have decreasing cost per bit, increasing capacity, increasing access time, decreased frequency of access to the memory by the processor. Now, fraction of accessing involving only level 1 hit ratio. So this is the average access time, and this is the fraction of accesses and involving only level 1. That's the ratio. Figure 1.15, performance of a simple two-level memory. Sweet. Now, principle of locality. Memory references by the processor tend to cluster. Data is organized so that the percentage of access to each successively low level is substantially less than that of the level above. It can be applied across more than 2 levels of memory. We have secondary memory, also referred to as auxiliary memory, external, non-volatile, and used to store programs and data files. Cache memory is invisible to the operating system. Yes, it is. Interacts with other memory management hardware. The processor must access memory at least once per instruction cycle. The processor execution is limited by memory cycle time and exploit the principle of locality with a small, fast memory. CPU will transfer CPU for cache, then main memory. Between the CPU and the cache is fast and includes word transfer, and between the cache and the main memory is slow, includes block transfer. So that's a single cache. A 3-level cache organization is a different story. So this is a figure of the cache and the main memory. Oh, sorry. Sorry. So here for the cache, we see the block length, the line number, the tag, the block. And for the main memory, we see memory addresses, the block, and so okay. So this is the structure of the cache and main memory. This so just take some time to appreciate and digest that. Also, this is a cache read operation. RA stands for read address. So here we have the start, receives address, receives address, read address from CPU. Does the block containing the read address in cache? No. Then you access the main memory for block containing the read address. Then you allocate cache slot for main memory block. Then you load the main memory block into the cache slot and deliver RA word to CPU. The fetch RA word and deliver to CPU. It's a block containing RA cache, yes. Fetch the RA word and deliver to CPU, then you're done. So just appreciate that flow diagram a bit. So, so this is a cache read operation, cache design. The main categories are the cache size, block size, mapping function, replacement algorithm, writing policy, and the number of cache levels. The cache and block size, the cache size, small caches have significant impacts on performance. Block size, the unit of data exchange between the cache and main memory, is the block size, yes. Mapping functions determine which cache location on the block will occupy. Two constraints affect design. When one block is read in, another may have to be replaced. The more flexible the mapping function, the more complex is the circuitry required to switch the cache. So for replacement algorithm, the least recently used LRU algorithm, effective strategy is to replace a block that has been in the cache the longest with no. Oh, excuse me. The least recently LRU algorithm, effective strategy is to replace a block that has been in the cache the longest with no references to it. The hardware mechanisms are needed to identify the least recently used block. It chooses which block to replace when a new block is to be loaded into the cache. The write policy dictates when the memory write operation takes place, can occur every time the block is updated, can occur when the block is replaced, and minimizes write operations. It leaves main memory in an obsolete state. Input-output techniques. When the processor encounters an instruction related to input-output, it executes that instruction by issuing a command to the appropriate input-output module. Three techniques are possible for input-output operations: programmed input-output, interrupt-driven input-output, and direct memory access. Programmed input-output. The input-output module performs the requested action, then sets the appropriate bits the input-output status register. The processor periodically checks the status of the input-output module until it determines the instruction is complete. With program input output, the performance level of the entire system is severely degraded. Interrupt-driven input output. Processor issues an input output command to the module and then goes on to do some other useful work. The input output module will then interrupt the processor to request service when it is ready to exchange data with the processor. The processor executes the data transfer and then resumes its former processing. It's more efficient than programmed input output, but still requires active intervention of the processor to transfer data between memory and an input output module. Interrupt-driven input-output drawbacks. Transfer rate is limited by the speed with which the processor can test and service a device. The processor is tied up in managing an input-output transfer. The number of instructions must be executed for each input-output transfer. Direct memory access, performed by a separate module on the system bus or incorporated into an input-output module. When the processor wishes to read or write data, it receives a command to the DMA module containing whether a read or write is requested, the address of the input-output device involved, and starting location in memory to read or write, the number of words to be read or written. Direct memory access. transfers the entire block of data directly to and from memory without going through the processor. The processor is involved only at the beginning and end of the transfer. The processor executes more slowly during a transfer when processor access to the bus is required. It's more efficient than interrupt-driven or programmed input-output. Now let's move on to symmetric multiprocessors, or SMPs. A standalone computer system with the following characteristics. That's what SMPs are. Two or more similar processors of comparable compatibility. Processors share the same memory and are interconnected by a bus or other internal connection scheme. Processors share access to input-output devices. All processors can perform the same functions. The system is controlled by an integrated operating system that provides interaction between processors and their programs at the job, task file, and data element levels. SMP has advantages. For example, performance. A system with multiple processors will yield greater performance if work can be done in parallel. Scaling, then, let's move from performance to availability. The failure of a single processor does not hold the machine. Incremental growth. An additional processor can be added to enhance performance, and as a result, that results in scaling. Vendors can offer a range of products with different price and performance characteristics. Processors include an L1 cache, L2 cache, processor, main memory, system bus, of course, interconnects all these processors and all these, the the processor, and the main memory and the input-output subsystem are all interconnected by the system bus. So this is symmetric multiprocessor organization. Multi-core computer, also known as a chip multiprocessor. It combines two or more processors or cores on a single piece of silicon die. Each core consists of all the components of an independent processor. In addition, multi-core chips also include L2 cache and in some cases L3 cache. So here's the block diagram. Let's just zoom in a bit. So 20 megabytes L3 cache, 4032 kilobytes, L1, 256 kilobytes for the L2 cache, 41, 42, 4041, all the way to core 6 and core 7. In total, this is a 20 megabyte L3 cache. DDR4 memory controllers, and a PC1 Express. This is just a block diagram. Shared cache, memory controller, 444, input output Intel Core, i7-5960, X block diagram. That's the physical layout on the chip. So in summary, the basic elements, evolution of microprocessor. This is just a summarization of what we went through. We went through the basic elements, the evolution of the microprocessor, the instruction execution, the interrupts and the instruction cycle, interrupt processing, multiple interrupts, the memory hierarchy, and cache memory, motivation, cache principles, cache design, then direct memory access, multiprocessor and multi-core organization, symmetric multiprocessors, and multi-core computers. Thank you for your time. Thank you for tuning in. And I'll see you next time to cover overview of another overview of the operating system. Chapter 2. Laters. Thank you. I'll see you in the next chapter, chapter 2.